from what Guy just discussed, we might be interested in doing something so that from sort of one thing we can get, we can optimize with respect to lots of different loss functions. So I'm going to show you another technique for doing something like that, and it does not use outcome indistinguishability, but it does use multi-calibration, and you can compare them. So you've seen from the first talk on multi-calibration, we were talking about multi-calibrating with respect to a collection C of sets. And then Guy talked about outcome indistinguishability. And instead of being outcome indistinguishable, so to speak, with respect to a collection of sets, it's with respect to a collection of distinguishers. And yet, especially at the first, there's this tight connection between sets and distinguishers. So now we're going to see a different notion of multi-calibration, which is multi-calibration with respect to a collection C of possibly real-valued functions. And sets are a special case because we can think of these functions as being the indicator functions for membership in the set. But it's just more general. And the idea is going to be that we're going to somehow multi-calibrate with respect to a collection of functions under some appropriate definition of multi-calibration. And the goal in this work is to multi-calibrate exactly once, and then for every loss function in a given set, show a big set, rich collection, show that there is a pretty easy to define kind of post-processing function, which can take the multi-calibrated value, post-process it to something else, and this new thing will minimize loss with respect to the desired loss function. At least it will do as well as any function C in your collection of functions. So you're not going to get beyond what you're working with, but you're going to kind of work once and then have post-processing in order to be competitive with everybody in the collection C. All right, so we're going to fix some arbitrary distribution D on instances labeled with 0 and 1. And our functions will operate on the elements of our universe X. So let's introduce the notion of a partition. A partition S, which is a collection of M disjoint subsets of X, is a collection of M disjoint subsets of X whose union is X itself. So here is a drawing of a partition. Now, in the most ideal world, these partitions would be the level sets of our reality P star. That's the dream world. This is not what happens. We won't be working with such partitions. But it would be really, really nice if we could. All right. Now, given a distribution D, we're going to let D sub I denote the conditional distribution conditioned on being in the ith cell of the partition. And now everything I'm going to say, it's almost always going to be focused on an arbitrary SI. Now, given a partition, we could define something called the canonical predictor. So what is this canonical predictor? S here names the partition. Okay? So F super S is just the following. Whenever you have an input X, you see which cell it is in, and then you produce the expectation within that cell of positive outcome, the expectation, the conditional expectation, E sub di of Y for X and Si. So by definition, because of the way we have constructed this canonical predictor, the cells themselves are sort of pieces of the level sets of the canonical predictor Fs. So for example, maybe in S1, the probability if we chose a random element in X1 that it would have a positive outcome, maybe that's 0.3. And maybe in S2 it's 0.2, and maybe over here in S sub m it's 0.3 again. So 0.3, these two slices, S1 and SM, are part of the, are like pieces of the level set of Fs. Yes?
Are you trying to show us with your...
What?
We're not seeing your pointer.
You're not seeing my pointer. I don't have a pointer.
Okay. I thought
Only when I actually write something. Thanks. Good. Is it clear what I was saying though? Since you didn't see a pointer? You're right that I was probably pointing at it thinking you could see something, but yeah. Yes?
How are you defining a level set?
Okay. Good. In my mind, thank you for the question. In my mind, I'm kind of, you're absolutely right. It's a perfectly fair question. So I'm imagining that our P star values are taken from some discretization of the interval 0, 1. And so for me, the level sets is like one of these buckets. So if your probability is, let's say that they are all multiples of 0.01. So if your probability is between 0.25 and 0.35, you get mapped to 0.3. Okay, good. Any other questions before I go on? Okay. All right. Good. Yes?
I'm a bit confused. You had the slide earlier that
What?
I'm a bit confused that in the earlier part of the slides you have the partition is not the level sets, but then you say it is?
No. Very good question. So I said in our dreams the partition would be a level set, and here I'm saying it is a level set. Different things. In our dreams, it's the level set of P star, the truth. We don't have the truth. Okay, so here we have some partition. Once this partition is fixed, I can define a function, and now these are the level sets of that function. And that's what's happening. Good. Anything else? Okay. So the new definition of multi-calibration, and I'll show you the list of authors of this work in a little bit, is the following. We say that a partition, not a function, but a partition now of the domain, is alpha multi-calibrated with respect to a collection C of functions and a distribution D, if for every cell in the partition, for every I, for every function C in our collection of functions, the covariance, when we look at the conditional distribution, DI, so just focusing on that one cell, the covariance of C of X and Y is bounded by alpha. So we'll go over the definition in a moment, but this is true for all I. We need this for all I. Okay? So let's recall the definition of covariance. The covariance on a distribution D of some random variables, Z1 and Z2, is the expectation of the product minus the product of the expectations. Okay. So, good. Now, for random variables x, y drawn from our distribution, where y is constrained to be either 0 or 1, the first claim is a simple claim to check. The covariance of x, y is equal to the probability that y is equal to 1 times the, I'm not sure what I should be doing here, times this expectation conditioned on y equal 1 of x minus the expectation without conditioning of x. Okay? And that's equal also to the probability when over d that y is equal to 0 times, now kind of switch the signs, the expectation of x minus the expectation of x when we condition on y equal to 0. And the proof of this, does anybody need to see the proof? The proof of this is pretty straightforward. So, great. Okay, so now, let's assume then that our partition, S1 up to Sm, is alpha multi-calibrated with respect to the collection C and the distribution D. Then, and that means that it satisfies this requirement. Then the claim implies the following. And this is really, really important. So it's just like the heart of everything in the paper. So it's not difficult to see, but be sure you get it. For every cell in the partition, and for every function C, and for every possible output B, the probability over di that y is equal to b times this difference, the expectation over di given that y is equal to b of c of x minus the expectation in general over di of c of x is bounded by alpha. So what is that telling us? That's telling us a whole lot. It's telling us that conditioning on y, on the value of y, doesn't really change the expectation of c by very much. So another way to think about this is, suppose I feed random samples x from di into c. C can't distinguish, it can't pull apart the cases where y is equal to b from the cases, from just the general population. And it can't pull apart the cases where y is equal to 0, 1 minus b, from the general population. So C can't do really any more distinguishing. Once we have multi-calibrated with respect to C, the game is sort of over. So, before we go on, let's go back to what we're trying to argue. We're trying to argue that there's this miraculous way of creating a function so that once we have this, if we wish to optimize one kind of loss, we can post-process and do as well as any function in our collection. And if we instead wish to optimize with respect to some other loss in this class of loss functions, then we could apply a different post-processing, and again, we would do as well as any function in the collection. So why, given this definition, given what I've shown you, why is this completely and totally not surprising? Because you're not really optimizing over the world at large. You're only trying to beat elements of C. But multi-calibrating with respect to C has caused you to lose any predictive ability about whether y is 0 or y is 1. C is all there is. Like average C is all there is. So, you guys may all be infinitely smarter than I am, and you may totally get this. If, nonetheless, you don't completely understand what's going on by the end of this presentation, go back and look at the paper and just focus on exactly what this is telling you. This particular part is telling you. Because this is really the heart of it. Everything else, I think, if I've understood it correctly, and I chose to talk about it today as a forcing function to try to be able to understand it well enough to explain it to somebody. If I've understood it correctly, there's just one more trick. So, let's go on.
Just one question. How can you ensure?
What?
How can you ensure that you don't have a pathological partition that the probability of like?
Well, I did multi-calibrate. So what do you mean by a pathological partition?
Like you have two parts of this thing according to epsilon and alpha, right? And you have the probability over this di to such that y equals this b is very small. So
Right. Okay. So if I have understood what you're saying, you're talking about this. Right? We might have that the probability that y is equal to b is very small. And we might have that if we chose, that we're looking at a particular slice in the partition that nobody shows up in. Or it's it has very small probability. So all of that is true. That was probably going to get swallowed up by the alpha.
Scroll up a bit.
What?
Could you please scroll back up a bit?
Sure. What do you want to see?
Where you wrote down the claim actually.
Here? More? More or not? Are we good? Yeah. Okay. But in answer to your question, this is the same issue that shows up all the time, the very light cases. All right, good. Now, comment. We're interested in multi-calibration with respect to subpopulations, populations of interest, demographic groups, whatever. So suppose we have a subpopulation T that is a subset of our universe. And suppose further that the indicator function for T is in our collection of sets. So again, this is exactly the same issue we've been talking about over and over. Which sets should be included? Multi-calibration with respect to what? We can't escape it. So if we want to handle demographic subgroups, we have to put their indicator functions into the collection. Okay. So if you do this, you can then define a new distribution, d prime, which is d conditioned on x being in this special subpopulation. Here's its probability, the distribution. Now, so what does that look like? This is like some cross-cutting piece in our universe, right? So this is the intersection with S1, this is the intersection with S2, and so on and so forth. And so this gives us, S1 prime, S2 prime, and these are these pink regions that I've drawn out. And then we can look at the conditional distribution conditioned on being in S1 prime, S2 prime, and so on and so forth. And the claim is that if S is alpha multi-calibrated with respect to the original C and D, then S prime, this new partitioning, which is on these regions, inside the gray circle, then S prime is also multi-calibrated with respect to the functions that are supported on T and are zero outside of T. And we know that this collection of functions is non-empty because we insisted that the indicator function for membership in T be in the collection. Now, we let C prime I have an extra infinity here, forget this one. C prime infinity, that's just the maximum over all C in this collection C prime of the absolute value of C of X. So the claim is that if S is alpha multi-calibrated for C and D, then S prime is alpha times 1 plus this max value over dx prime multi-calibrated for C prime and D prime. So that's how they handle and this is actually not a terrible proof, but it's not a 1 or 2 liner. But somewhere in there, we end up looking at the expectation of C prime of x, or no, C of x for some C and C prime. And that's where this term is coming from. All right. Good. So now we have defined what it means for a partition to be multi-calibrated with respect to a collection C of functions and a distribution D on data. Now let's talk about loss functions. I am giving you a weaker version of the results that are proved in the paper. So let me start by talking about a few different loss functions, not knowledgeably, just listing them, and then I'm going to make a distinction between 2 kinds, the dark blue and the light blue. Okay? So dark blue is the LP loss, binary classification loss, maybe with different false positive and false negative costs captured by that. Exponential loss function, and then logistic loss function and the hinge loss. What we need for our loss functions, first and foremost, they should be convex and they should be Lipschitz. These guys, oh, I've run out of power. These guys, these two are Lipschitz everywhere. The other guys, not so much. But there's some nice intervals in which they are Lipschitz, and moreover, their minima within their own special intervals are not much smaller than their overall minima. And so the full proof says, hey, we can even do some stuff for functions. We can do what we want to do for functions like that. So they have a notion of what it means for a loss function to be b comma epsilon nice. So these are convex loss functions, all of them. The b is a Lipschitz constant. And the epsilon has to do with minima inside the magic intervals and outside. And we're paying no attention to that whatsoever. We're only going to just think about things that are convex and Lipschitz everywhere. Okay. But if you look at the paper and you see that they're talking about all this stuff about clip, blah, 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 this clip involves like focusing everything to those special intervals. And if you have values that are out here, you just map them to the endpoint, the nearest endpoint of the intervals. Okay, so here's the author list. Gopalan Kalai, Reingold, Sharon, and Wieder. So now let's define formally what an omni-predictor is. I gave you the intuition for it earlier, that you should be able to get a prediction, and then for the loss function that you care about, there should be some post-processing that allows you to at least beat or do almost as well as any function in your collection C. So let C be a family of functions on X. Let L be a family of loss functions, the nice ones that we've been talking about. Actually, you can define omni-predictor without their being nice. You can construct them when they are nice. So the function F, mapping instances to 0, 1, is a L for the family of loss functions, C for the collection of functions, your competitor functions, so to speak. Delta is an error term, omni-predictor. If for every little l in your collection of loss functions, there is some post-processing guy that takes whatever it is your predictor says, which is between 0 and 1, gives you another number, and it has the following property. This term on the left is the expected loss if you k post-process F. This is the expected loss under the distribution D. So you have your predictor F. Now you're going to post-process it with a special K for this particular L. You get to use a different post-processing function for every L. But imagine that the instructions for post-processing are posted on the web, and you run the predictor, you get your number, and then you invoke the post-processing function that you need. Okay? So the term on the left is the expected loss of the K post-processed F under D. And the term on the right is the expected loss of the best function C in your collection. And again, best means best for this particular L. So what that says is that for every loss function, little l in our collection, there is some univariate post-processing of the predictions, just of the predictions, that is competitive. So let's get the order of quantifiers right. For every C, and for every L, there is a univariate post-processing of the predictions that's competitive now against all of the C in the collection. So quantifier is right. So just to see the ideal world, just as Guy is always saying, P star should pass any tests. So let's see what happens here with P star. So the claim is that P star itself is an omnipredictor. And let's see why that is. So P star is defined to be the expectation of Y given X. Now, given any loss function, we're going to define the post-processor for this particular loss function as follows. So my post-processor, remember, it's taking as its input the prediction that was made by the predictor, the omnipredictor. So that's a number between 0 and 1. So K sub L is operating on the unit interval, an element in the unit interval. So we take this to be the argmin over all T, all real T, of the expectation when we draw Y according to the Bernoulli distribution with probability P. So that's the same P. That's why it's highlighted in yellow. It's the expectation of the loss of Y on T. That's equal, by definition, to the argmin over T of P times the loss of 1 for T plus 1 minus P times the loss for T when we have 0. Now, finding this value, this argmin T, that's just a one-dimensional convex optimization because of the form of this equation. So there are a lot of algorithms for doing that. So again, we have our predictor. Our predictor is giving us a real number between 0 and 1. We have a method that is specific to the loss function L, a convex optimization in one dimension to give us the right value T. And why is this the right thing to do for P star? So condition on any particular value of X, my bold and my not bolded things are completely indistinguishable in this picture. Y is distributed according to a Bernoulli distribution with probability P star X of coming up heads. But this is Y star. This is what we've been calling Y star until now. That's its distribution. So that means that KL of P star on X minimizes the expected loss, the true expected loss, because this is its true behavior. Now, for all X, then we get that the expectation of D conditioned on seeing this particular value of x, of the loss of y, KL, P star of x, is then less than or equal to the expectation over all, on the same conditional distribution of L of y, C of x. Why? Because P star of x is really the truth. It really is, you're really not going to do any better than that. That is your best loss. That's coming from this line. So that means we immediately have this. And now we average over all of the x and we get what we want. Okay. Good. So P star is an omni-predictor. It's an omni-predictor, in fact, with delta equal to 0. There's no slack here. Of course, as always, we don't have P star. We can't use P star, so we need to do something else. Okay, so let's remind ourselves. We have our distribution D on x cross y. We have a partitioning of the x's into S1 up to Sm. And we defined what, did I define the canonical predictor? Did I? No, let's define the canonical predictor then. What did I define? Oh, well, the canonical predictor, F super S. So this again, this S is the partitioning. I have to lower this to where I can reach it with my pointer. Okay, so this S is our partitioning. So what is it? F super S of x. Are you sure I didn't define this? It's the expectation over, for when x is in Si, it's the expectation of di of y. Okay. Yes, it says recall here on the slide. I did say it. Okay, good. So let's just take a quick look at this for a moment. Everybody in Si is being given the same value. This is the expectation over this slice of the outcome, or the fraction of this slice that has positive outcome. So this is a constant on each slice. So let's call it Pi, and it is indicating that this is the fixed constant prediction for the canonical predictor on the ith slice. Okay. Good. So now, assuming we have our nice convex Lipschitz loss function L, I'm going to take the canonical predictor and I want to adjust it for L. Different adjustment for each L. So we're going to call this the L-adjusted canonical predictor and denote it F super S sub L of x. And this is our old KL, the same KL we saw before, composed with Fs of x. So again, KL of P, for any number P, KL of P is just the argument T of the loss of y, I don't know how to say it, the loss of y and T, where y is drawn according to the Bernoulli distribution P. Okay? So the next claim can be interpreted as the L-adjusted canonical predictor rules. F super S sub L is the big winner. What does it say formally? Suppose we have any function, and you have to parse this a little carefully. It maps whole slices to a real. So it's going, anything that's going to be constant on a slice. And the claim is that for any such h, the expected loss for the L-adjusted canonical predictor with respect to D is at most the expected loss for this H with respect to D. So again, the loss is smaller on the L-adjusted canonical predictor. Hence, FSL rules. So the proof of this is as follows. For every I, we know by definition that the y's for the x's that, I'm sorry. Tell me if you have any question about that. If I draw y according to di, then that will be distributed as Bernoulli of pi. The distribution on y's is Bernoulli of pi. That's kind of how we chose pi in the first place, how we defined pi in the first place. So, the expected loss for the canonical L-adjusted, the L-adjusted canonical predictor for di is the expectation when we're drawing Bernoulli, Bernoulli, according to Bernoulli of pi, of L of y and KL of pi, where KL is our adjustment function for this particular L. And then that, the claim is no larger than this amount. That's what that's because KL of pi is in fact the best answer for L. It's the argmin. So this is at most the expectation according, drawing y from Bernoulli of pi of L of y, h of this slice, whatever this constant value is that h gives to the slice, and that's the expected loss of h on that slice. So if we have an alpha multi-calibrated partition, we know what to do given a loss function L. That's what that says. And that's what the theorem is going to say. So what is it? Let's go over the theorem. Let D be a distribution on x cross 0, 1. C a family of real-valued functions. And script L the family of all B Lipschitz convex functions. Then, if the partition S is alpha multi-calibrated for C and D, then the canonical predictor is an LC, and then it's got these other parameters. The parameters, roughly speaking, the 2 is coming from considering the case of y equals 0 and y equals 1. The alpha is coming from kind of the covariance gap on each slice. And the B is coming from the Lipschitzness. Like you'll see where that comes in. So it is an LC2 alpha B omnipredictor. We're not going to prove the whole key lemma, but we're going to highlight, and the key lemma has a lot of stuff in it that has to do with those intervals and things like that that we are ignoring. We're going to highlight the main point that you need to know. So, the key lemma says the following. Given a loss function in a C, I'm going to define a new function called C hat, which again takes slices to real numbers. And C hat, now remember, C is it has all of our competitor functions that we need to beat in the omnipredictor. And it may have some other functions in there as well, like what's it called? The indicator function for various groups of interest, and who knows what else. So for every C, I'm defining a C hat. And I'm kind of emphasizing this because if you look at its shape, it's reminding us a whole lot of the canonical L predictor. But inside, I'm out of power here, but inside we have C. which just happens to be one of the functions in our collection. So for every C, we define C hat to be the expectation over D. I'm just doing this one slice at a time, so the ith slice. The expectation over the conditional distribution, DI, of C of X. Okay? So then, the claim is that the expected loss, no, there are two pieces. The expected loss of our new C hat on D is no greater than the expected loss of the original C on D, plus some change. And we've discussed where that that change is coming from. So how do we prove this? First of all, look at these two quantities. So we have L bar of CD, and we have L bar of C hat D. The expected loss of C on DI is the expectation over DI of the loss for Y and C of X, by definition. So that's the expectation over Y from DI of the expectation over X conditioned on this value of Y, of the loss of Y in CX. Now, our loss functions are convex. They're convex in their second argument. So the convexity of L and T says we get to move this expectation inside the expectation of Y of DI, L of Y, and E of expectation of X on the conditional DI conditioned on Y of CX. Okay. Now let's look at expected loss for C hat. The expected loss for C hat, plugging in the definition of expected loss, that's the expectation for Y in DI of the loss of Y of, well, what is C hat of X? It's the expectation over X in DI of C of X, by definition. Now, look at these two terms that are underlined in yellow. What do we know about them? What did we identify about them really early on? And I said, this is the heart of the entire argument.
How we have the probability difference of the expectation is smaller than alpha.
That's right. They're close to each other. They're really close. That any major difference here would mean that we hadn't wrung all of the utility out of C, and C is now going to be able to separate things out for us, and it can't. So here we've conditioned on some particular value of Y. Here we are not conditioning, and we said before there's no real difference, or it's a small difference, or it's bounded by alpha, whatever. So recall then exactly that multi-calibration of S with respect to C and D says that these two terms are very close. And now we get to use the fact that L is B Lipschitz. Oh gosh, I wish I could remember. Oh right, it's B Lipschitz. So it's B times the difference between these two terms I can't reach. It's going to be B times the difference between these two quantities. That's where our B times alpha is coming from. So these guys are close. And in a little bit more detail, this is the whole argument. The 2 is coming from the fact that we're looking at yi equals 0 and yi equals 1. And then these differences are bounded by alpha. Alpha? Yeah, are bounded by alpha. There. Good. Okay. And then we have the B that comes from the Lipschitzness of the loss function. So we're almost done with the main theorem. And the last statement is that, let's see if I can remember what this says. The expected loss of the L-adjusted canonical predictor is bounded by our FSL rules claim, bounded above by the expected loss for C hat and D. And remember that then we can do this because C hat maps whole slices to the same value. And then by the key lemma, this quantity is bounded by the expected loss of C on D plus the change. So that's the story of the omni predictors. Yes?
Does the KL that we use, once we have our trained predictor, is it the same as the KL that's the one for P star? The post-processing function?
Yes, the post-processing function depends only on the loss function that you wish to be that you want to minimize.
Okay.
So again, you want to post-process the prediction from the predictor we built, so as to be competitive in terms of this particular loss function with respect to any C in the collection.
What does that post-processing look like?
That post-processing is that one-dimensional convex optimization.
Oh, but like if I took like the L1 loss or something, does it have like a easy, is it like thresholding or something? Okay.
Does somebody know? I don't know. Oh, so for L1, I think we do know, right? You even mentioned it this morning.
I think it's thresholding and a half.
Right, thresholding, right. Mm-hmm. Yes. And for L2, you just take the prediction itself and whatever. All right, so that's what I wanted to tell you about. That's it. Okay. We're done.